Hi folks, I'm Jennings and I'm going to be talking to you today about an experiment that Jim Davies and I conducted, which was published in the Proceedings of the Cognitive Science Society in 2017. This experiment focused on embodied cognition and folk physics, which we think has shown that the motor system doesn't use a curvilinear impetus belief. Now you're probably thinking about closing that window, but bear with me, it's actually much more interesting than the name implies. So, let's get a couple definitions out of the way so that the title actually makes some sense. Folk physics is the systematic discrepancy observed between the ability to do a physical task and the inability to accurately describe or depict it. So for example, if you ask people to crawl, they're able to do so easily, much like you can see Spidey doing here. And they've been able to do that since they were a baby. But if you ask them to describe how they did it, the error rate can be actually quite high. So many participants say they moved their left hand, left foot, right hand, right foot, when in fact they just crawled moments before in an X fashion, moving their left arm, right leg, right arm, left leg. So an example of this kind of misconception that's quite popular is the curvilinear impetus belief, which is easier to show you than it is to describe it. So let's take a closer look. So I'm going to show you two dynamic examples, and only one of these reflects how inanimate objects move in the real world. So take a guess at which one you think is correct, and you've got a 50-50 chance. Well, if you guess the one on the right, you're correct. Now, the one on the left is curvilinear, and it's not the way that actual physics works. But don't feel bad if you guessed wrong, as I'll explain in a minute. So, the curvilinear impetus belief is the incorrect assumption that an object traveling in a circular motion will continue this curved path upon exiting a spiral. So previous research had shown that participants were not very accurate at predicting the trajectory of where a ball will go. Once it's shot from the middle part of a spiral to go through the end of the spiral, where it will take after that, its trajectory. But these preliminary studies, these preliminary experiments, they were done with paper and pencil, which is an inherently artificial task when it comes to object motion. And furthermore, if you do the same experiment but tell participants that it's a coiled hose with water rather than a ball and tube, they're more accurate. And this led the researchers to think that the abstractness of the task itself was increasing the error rate. And interestingly, when participants were shown some moving stimuli, much like the ones I just showed you, they weren't significantly better at choosing the correct trajectory from the paper and pencil group. So what other factors here might be influencing accuracy? Well, it was thought that physical touch might have been necessary to improve accuracy. So physical touch was included in another experiment where participants had to push a puck through a curved shape, much like the animations here. Now this could be accomplished if the puck was pushed through straight, like the top animation, but many participants tried to perform a curvilinear action like the bottom one. And the ones who did it correctly, like the top, in a post-test questionnaire, they were quite ready to suggest that a curvilinear strategy might have worked as well. So physical touch does improve accuracy. It did improve accuracy, but a quarter of the participants, they're still using a curvilinear strategy. Relatedly, research has shown that people can accurately grab two identical sized objects while simultaneously perceiving one as larger. Now this suggests that the motor system of the brain is not fooled by perceptual illusions. However, these illusions are a little different from the curvilinear impetus belief problems since they're not visual illusions, but they're internal misconceptions involving real-world object motion. And this misconception seems to form the basis of our understanding of object motion. Now, this may seem silly today, but it was a dominant theory of physics in medieval Europe, where objects had their own impetus or force or energy by which their bodies moved. So this suggests that the curvilinear impetus belief is not a learned misconception, but a default physics by which we interpret the world. In fact, even physicists fall back on curvilinear impetus beliefs when they're under time constraints, when asked to solve the same spiral diagrams. So if you picked the wrong trajectory a few slides back, even physicists do it, so don't feel bad about it. Now, that's a little background out of the way on folk physics and curvilinear impetus belief, so we can talk about embodied cognition, and specifically how it's different from traditional cognition as it's been thought of, mainly models and representations. So we've seen that many experiments tested impetus beliefs using abstract stimuli and some dynamic and some physical stimuli. However, the difference between what has been done in the lab and what happens in real life is the difference between predicting or producing and reacting. In the previous experiments, participants were producing or predicting trajectories rather than responding to them. For instance, people do not regularly predict where water will exit from a coiled hose, but they do respond to it physically and accurately without effort. So this cuts to the heart of a bias within cognitive science, that all processing is done by symbol manipulation in the mind. Now, there is an alternative approach suggested by research in embodied cognition, which would state that the ability of the motor system to respond to moving objects has traditionally been explained with complex abstract terms, but it's easily accomplished with simple embodied perception action rules. So, we have to pit these two against each other, and a good way to do this is the outfielder problem, which simply asks, how does an outfielder catch a fly ball? So the representational approach, the one primarily used in cognitive science, would say that the outfielder has a model and applies abstract rules on how to catch it. So first, the player would calculate the initial speed and angle, use laws of projectile motion to predict where the ball will land, and then move there in a straight line. Now, the embodied approach would say that the outfielder knows they follow two simple rules, perceptually based rules. So they move in a curved path that mirrors the path of the ball so that it looks like it's moving in a straight line. And second, match their speed so that the ball appears to be moving at a constant velocity. Now, the embodied cognition approach seems to have a simpler and arguably more natural account of how we engage with object motion. And furthermore, outfielders usually catch fly balls by running in curved lines. And to add further support to the embodied approach, people can catch fly balls that have physically impossible trajectories in virtual reality, both of which suggest a reactionary and embodied explanation. So, how do we account for the errors in these spiral diagrams? Now, one way is to propose a dual pathway for object motion. So, rather than the abstract and embodied distinction, Tresillian in 1995 proposed a dual system of object motion that is treated separately in the mind, using different mechanisms to process information. The cognitive perceptual pathway, as he proposed, would deal with abstract information based on prediction or using rule-based algorithms, whereas the action-oriented pathway mirrors what embodiment researchers have called the perception action loop. So this action-oriented pathway would consist of simple, automatic, and reactionary rules that utilize relational information between the body and the environment. With this in mind, the errors observed in folk physics research may be due to the cognitive perceptual pathway processing information that is more naturally suited to processing by the action-oriented pathway. In Tresillian's model, the errors that are observed in curvilinear impetus belief problems are the result of the cognitive perceptual pathway being forced to perform an inherently artificial task that it's not biologically suited to. Whereas a real spiral and ball would have the action-oriented pathway perform as intended, quickly, accurately, and situated in the real world. So a cognitive perceptual pathway set opposite to an action-oriented pathway would account for all types of object motion perception, as well as the errors observed in the literature. So, our present study aimed to test this by increasing the level of embodiment over three conditions. The increase was done across three conditions. We had an abstract paper and pencil task, similar to previous research, a medium embodied condition, also called a prediction condition, and an embodied condition, which we referred to as the action condition. Now, we hypothesized that participants in the paper and pencil task would perform the worst, with participants in the action condition performing the best, and the medium embodied condition would fall somewhere in between. So the paper and pencil condition would use the cognitive perceptual pathway. and the action condition would use the action-oriented pathway, and the prediction would use both. And they look something like this. So for the paper and pencil task, participants had to draw a trajectory that they thought the ball would take. So participants in the prediction condition, they had to choose from a set of pre-drawn trajectories that looked to be coming out of the actual physical spiral. And participants in the action condition had to reach for the ball only when it passed the marked area in red so as to catch it in the palm of their hand. So the spiral, just to give you a sense of how big it is, looks something like this. The participants were sat beside it, and they had to reach their hand out once the ball was very close to exiting the end of the spiral, and it moved pretty fast. So it went something like that. Oh, so fast I dropped it. The curved lines that were drawn in the paper and pencil task, these were taken to be categorically as incorrect, and straight lines that were drawn were correct. So curved lines were incorrect for the paper and pencil and prediction conditions, and the participant's hand was, if it was more than 1 inch outside of the correct trajectory, measured from the knuckle, then it was also incorrect. So, what do we find? Well, we found some significant differences between all conditions overall. So between the abstract and prediction conditions and the abstract and action conditions and the prediction and action conditions. But we were surprised to see that the differences were not in the stepped manner as hypothesized, as the prediction condition had the lowest accuracy of all. So, what does it all mean? Well, we found that the degree of embodiment did affect accuracy, but not in the predicted way. We also noted that most of the participants in the prediction condition chose D or E. The paper and pencil condition had slightly higher accuracy than previous studies, but upon reflection it may be a more embodied cognition than the prediction condition. The act of drawing the trajectory may allow the motor system to be recruited enough to improve accuracy, while in the prediction condition there wasn't any participant movement. Furthermore, the low levels of accuracy in the prediction condition may be due to the action-oriented and the cognitive perceptual pathways fighting for precedence. If both pathways were activated at the same time, they may cause interference and cause the accuracy to be compromised. So, from such a simple study, there's a lot of places to go from here. Future research could expand the prediction condition of this experiment by investigating how participant motion, for example, pointing to the correct trajectory or producing it alongside the spiral, might increase the number of correct responses by activating the action-oriented pathway. Other areas of research may include asking participants to imagine or visualize the trajectory of the ball before choosing or drawing their prediction. This may more accurately determine the capabilities of the cognitive perceptual pathway. It would be beneficial to measure velocity of hand movements to determine if there is an incorrect prediction and the motor system is correcting for it on the fly. And it would also be interesting to use VR to have many different trajectories to see if participants are more accurate catching correct trajectories, curvilinear ones, or equally equipped to catch both. So to sum up, there were some limitations. The data was categorically analyzed, which meant that the accuracy is more coarse than might be hoped for. And I only gathered one data point for each participant. And finally, the level of embodiment in the three conditions may not have been accurately depicted, as the stepped increase that we hypothesized was not seen. So, thanks for listening, and I hope I've clarified any potential questions, but if you have any, let me know in the comments, and I'll try and respond. Also, click the link to read the full paper. Thank you.